Welcome to Study Loop.
We are given a diffraction grating with line density 5000 per centimeter, and the width of the diffraction grating itself is 3.5 centimeters. So the total number of lines on the diffraction grating is the density times the length, which is 5000 times 3.5, which is 17,500 lines. So that now we know that chromatic resolving power is lambda by delta lambda, and for a diffraction grating, that is Nm, where n is the number of slits and m is the order at which we are resolving. So for order 1, it's simply n, which is 17,500. Now that we have this, for part B, we want to see if we can resolve the sodium doublet line. Sodium doublet line has the wavelengths 589 nanometers and 589.59 nanometers. So lambda is any of these. So delta lambda is the difference, which is 0.59 nanometers. So now the chromatic resolving power is lambda by delta lambda, which is, now because the difference is so small, for lambda we can consider either of these. So that's 589 divided by delta lambda is 0.59, which is almost 1000. So because our resolving power is larger than this, we can successfully resolve the sodium doublet. Now part C has multiple questions. The first thing to note is that we are operating at order 2 now, so m is equal to 2. Now we are zooming in at the wavelength 587.8002 meters. I'm sorry, nanometers. So delta lambda by lambda, we know, is 1 by nm, which gives us delta lambda is equal to lambda by nm, which is 587.8002 by 2 times 17,500, which turns out to be 0.0168 nanometers. Hence, the minimum wavelength that we can resolve above this wavelength is simply lambda plus delta lambda, which is 587.8002 plus 0.0168, which is 587.8170 nanometers. Now similarly, for part 2 of part C, the wavelength we can resolve below the wavelength is lambda minus delta lambda, which turns out to be 587.7834 nanometers. Hence, the range of wavelengths that cannot be resolved is 587.7834 nanometers to 587.8170 nanometers. This is the range of wavelengths that we can't resolve using our diffraction grating.